Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. Lots of materials conduct electricity when you shine a light on them. Think ordinary metals or solar panels, where electrons begin to flow through the material when you illuminate it. But here's a basic question. When the light hits the material, what path do the electrons take? That's what drives physicist Nathan Gaber's recent work at the University of California, Riverside.
There are these kind of paths of least resistance that the electrons would take. So when I put an electron in, it actually follows that path. And we wanted to be able to image those.
But Gaber's team didn't just want to image the electron flow. They also wanted to steer the electron's trajectory. To do that, they designed a unique micron-scale device. They took a crystal of yttrium iron garnet, which does not conduct electricity, and put a nanometers thick layer of platinum, which does conduct electricity, on top of it. When they illuminate the device with a laser, this device produces an electric current, as desired. It also turns out, when you combine the crystal with the platinum, the interface between the two materials exhibits some surprising magnetic properties.
You take a seemingly boring insulator and you take a regular metal, platinum, but when you glue them together and you have this very, very, little narrow interface between the two, they actually become sensitive to a magnetic field.
Gaber's team used this sensitivity to a magnetic field to steer the electron flow in the device. Specifically, the direction of the electron's motion responds to the magnetic field according to a phenomenon known as the Nernst effect.
So we heat with the laser, and that generates the current, and that creates a temperature gradient. And then I apply a magnetic field, and then the Nernst effect says that if the magnetic field's in one direction, then the direction of the current flow is perpendicular to that.
In addition to creating the electric current in the device, the laser light also allowed them to image the electron flow in the device. They mapped the electrons' paths while varying the direction of an external magnetic field. Gaber likens these paths to fluid streamlines, such as air around an airplane wing. These streamlines map out a sort of average path that the electrons take in the material.
It's just like you would think with wind. We would say, the wind is traveling at 5 miles per hour to the west. But really, inside the wind are all these little microscopic particles that are kind of colliding with each other in random directions at all the time, but they have a net flow that is 5 miles per hour to the west. So it's the same exact thing. It's that those flow lines show the kind of net flow of these electrons as they would diffuse through the material.
They found that they could make the electron streamlines squeeze or contort around the device by changing the device's shape, much like you can change the airflow around an airplane wing by changing its shape. This technique enables them to analyze electron flow, which could lead to more efficient electronic devices.
Even in conventional materials, when electrons get bunched together, they heat up, and that's actually what causes devices to die. So you could actually use a technique like this to optimize the shape of devices to kind of make them cause less heat.
Gaber is interested in applying this current imaging technique in exotic materials, such as those where electrons form vortices and eddy currents. This work was published in a recent issue of the Proceedings of the National Academy of Sciences. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X @MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.